Yes, thank you. Thank you for the sound check. Oh, yeah, thank you. Yeah, I think you hear me when I talk. My dog may make a noise, but that's not me.
Miss Dewberry, how do we put answers into the quiz?
If you're having difficulty, go ahead and put it on a sheet of paper, and you have until 6:15 to send it by. I would take a photo of it and send it to the FSCJ number. I think it's not as dark when we go that route. If all else fails, call my cell phone and leave a text message by 6:15, or give me a verbal answer on my cell phone. That'll store it for you and meet the time deadline. That's for everybody that's having trouble.
Can I ask a question about one of the questions?
No, sir.
Okay.
That's the problem. Do your best. This
Okay.
is an administrative quiz. We're learning from it. Don't panic.
Miss Dewberry, I have a question about something.
Pardon me. Let me go get my dog. I'm sorry. Thank you. Oh. Yes, ma'am. Somebody had a question.
Would the final exam be, would it be considered a test, or is that separate?
Oh, yes. Well, that's what a final exam is an evaluation tool.
I'm just asking because for question 1, it's asking for the...
No. I shouldn't even answer it because it's a quiz. Do the best you can. Yeah, this is a learning quiz. Okay?
Okay.
It's not going to fail. It's not going to fail you if you don't do well on an administrative quiz. But thank you for asking, because everybody could hear the answer.
All right, can you guys hear me?
Yes, I got you. Don't forget the quiz is due by 1:45. I think I said 6 something a minute ago.
Oh, what? How do I get there? Yes, ma'am.
Click on the quiz, which is when you get to the home page, it should be in the column on the left. It says quizzes. Oh,
Okay.
thank you. Thank you for the refresher.
Oh, shit. Oh. Okay, thank you.
This is just an administrative quiz to kind of test it out. Don't panic.
Right.
Yeah, most of the first week is going to be a little trial and error.
I was like, it's the second day. What the
Pardon?
I said it was the second day. Like, holy cow.
I know. It tells you more than you need to know because I want to be very explicit. At least you can laugh about it. I appreciate that.
All right, thank you.
At least it's not raining and lightning today.
I know.
And I also understand that someone in the class apparently had hail. I'm glad we didn't have that.
Were they in Florida?
I know. Yep. Ladies and gentlemen, some of you might be taking quizzes and still on conference. That's fine. I am going to flip through my PowerPoint to make sure we can get through some of it. And we do have about 2 other lessons after this, of which are a little bit shorter. So pardon me, but I'm going to be probably changing the screen rather rapidly. So just take your time. We have until roughly about 1:40. We'll probably start the lesson after everybody's completed the quiz. Well, that's not too good.
Oh, yeah. We text you the answers. Okay.
Yeah, thank you for reinforcing that.
Thanks.
Oh, you're welcome.
Professor,
Yes.
is it okay if we email it to you or text it to you, or is it just one or the other?
It doesn't make any difference, whichever is convenient for you. Text and email stay permanent on my phone. I have a cloud attached to my phone, so that's not going to be a problem.
Perfect. Just wanted to double check. Thank you.
You're welcome. Mm-hmm.
Professor, I am so lost. I've looked for the syllabus. I've looked through the files. I've looked through home. I'm looking
The
through
file
notes.
is Epson 18.
Epson. Okay. All right. My bad. Thank you.
Thank you.
Where can I actually find the
It's
syllabus?
on the homepage as well.
It is? Okay. I'm looking at the homepage and I'm still not able to find the syllabus. See the link.
I don't have a
to the
syllabus. Yeah, I have nothing in syllabus. You need to go to the home page and look at individual entries.
Oh, I remember. All right. Thank you. Thank you.
Good, good. Well, that's what we're doing this week, trying to reinforce your memory. You did good.
Thank you.
You're welcome.
Would you like us to email this to you or?
Okay, I should have printed something you should be able to read. Under Dewberry, it says, yeah. Let me see if I can find it. Email the answer or text message quiz answers. Okay. You can always do that, either on my phone or on an email through FSCJ is probably better.
Yes,
But
ma'am.
I have no preference. Yeah, it might be easier to do FSCJ, but if you don't want to mess with your screen, put it on your phone. That'd be great. Not a problem. Not a problem. Text.
You said you prefer your FSCJ or your Gmail?
FSCJ apparently keeps it a little clearer than my cell phone. Some of the photos and text messages appear to be a little dark on my phone, and but if you just write something out, the text looks okay. For some reason, I don't know why that does that.
Sorry to be a stickler, but do you have like?
Oh, no, no, we got to get the kinks out of this thing this week. Go ahead.
Some of my professors would get very upset if I didn't specifically put my first and last name and then the class number, the 3 letters, the 4 digits, and then the C at the end. So how do you want us to do the subject so you can organize this finally?
Well, I hope you put your name on all the papers.
All right.
And I can tell from the problems or the quizzes you're taking what course you're in. Maybe they just have the same course 5 or 6 times and they need to know which one you're in. It would be nice if you just maybe said, type your name or say your name and just say Physics 1 and that's your 2048 C class. Don't need to do a lot of typing. But I'll know from your last name what class you're in because nobody's taking both classes.
Sure, and there's no problem with that level of complexity either. I was just, they in particular would get very mad. Noticed.
Well, some professors, especially in communication, have 3 classes of the same thing, and their classes are not limited like it is in science. Sometimes they'll have 35 students in every class. So I understand why they have to be very exact. But I don't believe in doing that. It's unnecessary. It takes time to type and that kind of stuff. So.
Do you count quizzes as testing?
I'd rather not answer that because I'll be answering your quiz.
Well, isn't this the time for
There,
quizzes?
there's a reason. There's a reason why I asked the questions the way I did. Just do your best.
Okay.
Miss Dewberry, is it okay if I typed out my answer instead of writing it on a piece of paper?
Oh, that's fine. In fact, that's better because when you take a photograph of your writing, sometimes the page is darker than it should be for reading and grading purposes. I've sent a number of emails to people when that happened. I'm looking now at the emails at FSCJ, and it looks like it gives it a little bit brighter. So if you take a photograph, send it through the campus email because it's somewhat lighter than my phone, and I'm sure that's because it's on my phone. So thank you for
Okay,
asking.
thank you.
Yeah. Oh no, oh no, give it back to me. Come on.
So we just chill out till 1:30?
Sorry?
What if everyone's done?
The quiz will automatically turn off at 1:30. It gives you 15 minutes to get your answers to me.
I emailed them to you. Did you get it?
I'm prepping for the lesson, and I won't see it until probably tomorrow morning. Since I have a class after this class also. We have about 2 students that haven't logged on yet, so we will plan to start our conference discussion in about 1:45, everybody. I like a conversation going on between everyone. That's good.
Is anything else happening?
We're just waiting for 2 people to come to the conference. Yeah. According to the current enrollment, we're missing 2. So we'll wait until 1:45 for them, and then we'll get started. Some of you might want to practice writing on the page. In fact, somebody's already put hi, and I put the exclamation point. But don't anybody use blue. I'm going to use blue. And unless you want to point out something on the lesson, please don't write on it. Thank you.
I don't have the option to write on the board anymore. There was a little pop-up on the side, but it won't let me do that anymore.
That's okay, because it's better if I'm the only one that's doing the writing. Because if you go back and do white, you'll go over my original PowerPoint, but of course it won't stick. You're not, erasing anything permanently. I did all this trial and error stuff last week. In fact, I'll get rid of the exclamation point.
All the homework
everything.
is due the day of the next class period at midnight, right?
Almost. Occasionally I have homework due on Thursdays, but I usually give students a week to do homework, which means they're due usually by Tuesday. You might want to go through the calendar and see if there are any that are due Thursday, but almost all homework is due Tuesday night by midnight. That's so that students that have to work during the weekend can do it during the week. Students that work during the week can do it during the weekend. It gives everybody kind of a fair shot at time per homework. You may always turn it in early. That's the by due date. You can turn it in whenever you finish a question or a problem. Well, they're all problems, so. I'm going to go ahead and start. We waited about 12 minutes or so. I'm guessing that maybe they lost their way. Everybody here? Just say yes. Hello?
Yes, I'm here.
Okay.
Yes.
Good, good. Very good. Oh, yeah, good. Obviously, this is motion in one dimension, which is the topic for Chapter 2. If someone cannot hear me, would you speak up? I think everybody hears me then. Most of my PowerPoints begin with a page like this to give you a clue as to where in the text it's related to. However, our discussion of motion here at the beginning of the course is confined to constant acceleration. Now, you and I both know that when we drive a car and our foot is on the accelerator, it does not stay in one position. If it did, it'd give you leg cramps. So you really kind of move back and forth on the accelerator, and you're changing accelerations, you're decelerating, you're not accelerating at all when your speedometer reads the same speed. So it's a little bit difficult to picture all of the intervals of motion here involving a constant acceleration. However, that's exactly what it does, particularly because it is parabolic in nature or linear, maybe at a constant slope, but nonetheless linear. Our first page starts talking about some of the limitations and some of the definitions of what we're currently studying in Chapter 2. The study of motion is divided up into two methods, dynamics and kinematics. Dynamics is really what causes the motion. Kinematics is describing it. We do not talk about the cause of motion first because we have to know the language of kinematics, the symbolism of kinematics. What do the symbols mean? Physics and engineering primary are disciplines that require communicating by symbols. And to understand what the symbols mean for your situation is critical. Again, we will be using the center of mass or the center of gravity as we study chapters 1 through the first 2/3 of chapter 9. Now, I can imagine me driving a car that's a point mass. In fact, I can assume that I am sitting on the center of mass of the car while I'm moving. We will, however, extend our objects to extended body when we get to chapter 9. That's a little more practical. We will be, of course, talking about particle masses, which are dimensionless and certainly are a point on the page, like my pointer here, little dot. In order for motion to occur, obviously some kind of distance must have been traversed. A measure of that distance with a direction is called a displacement, which you probably encountered in your first course in physics. Most of the time you were dealing with constant accelerations in that first study, and you didn't deal with functions. Toward the end of today's lesson, we will use calculus and a function, and I hope you can see how it's related to the graphic nature of what we're doing. Displacement in equation form in the x direction is giving a delta symbol, which means a change in, but in physics, it means to take the final displacement, in this case, capital X sub small f, and always subtracting the initial position in X. No Y, no Z. In fact, X could be in the X sub initial, could actually be in the negative direction on a number line. So you could have a minus for the equation and a minus for the actual value X sub I. That statement is also true for the final position X. Obviously, these are units of meters, centimeters, and feet. So those are the standard units used in the text. Now, what is average velocity with respect to displacement? Literally, it is that delta D sub X. It's not X sub initial. It's not X sub final, but it's the final position minus the initial in the X direction. That displacement, even if you went for a walk and came back to the same position, your change in position is 0, your average velocity was 0. That's the way it's defined. And of course, divided by the time to travel that displacement. In symbolism, notice that vectors are bold-faced. At the beginning, it also has an arrow over it, implying that it is a vector, as we will see in Chapter 3. And it has a bar over that, which implies or is telling you that it's the average value. Now, we already know there's something wrong with average value, because if I go walking my dog and I come back, I have traversed a distance. But when I considered direction, it was like I never left my house.
Professor, why is there an arrowless line above the sign for velocity?
That means it's a vector. That means it's a vector.
Okay.
In other words, if you had a numeric answer of 5 meters per second, you would have to give me a direction. Yeah, good. Okay.
It's got an arrowless line over an arrowed line. It's got 2 lines above it. Why is that?
Of course. Yeah. One line is the arrow, which means it's a vector. And the other line is saying it's the average value. Some books put V sub X, and then they have an AV sub X. Your book doesn't like double subscripts.
I'm sorry. Why does it have 2 lines?
Pardon?
This says average velocity X equals displacement / time to this to travel displacement equals Vx, and that Vx has got 2 lines above it. What's the deal?
Well, the arrow means it's a vector, and the line over the arrow means its average value.
Oh, all right. Thank you.
Now, sorry. Some books want to do V sub X sub AV. We're going to find out why we don't want to use this, because I just gave you an example of I did some traveling, came back to my original position, and my average velocity was 0. So we got a problem with that definition. But let's move on, because we'll also elaborate on it. Of course, with the units as listed there. Now, the next slide really is what the average velocity would be if I had graphed some data of some kind of motion, and that motion, of course, would be represented as some kind of constant acceleration or deceleration or something like that. Excuse me, I'm going to have to get a drink of water. This particular line from time t equals 0, which is where the abscissa and the ordinates meet there in the lower left-hand corner, the blue line represents a car of some kind that was traveling very rapidly and then started, for instance, took their foot off the accelerator and allowed the car to come to rest at some t final. The best example I have of this, and of course the book starts with the car starting from 0. I'm not going to do the same thing as your text, but I will show you the 5 possible intervals of constant acceleration, increasing or decreasing. A good example of this would be if you had a garage that you had a door open to the backyard and a door open to the street. And your car was parked in your backyard with the garage doors open, and you raced through your garage, and as soon as your center of mass passed through the door to the street, you took your foot off the accelerator. Because of the computers used in cars now, and to save gas, as soon as your foot is off the accelerator, your car will begin to decelerate or slow down in fairly equal intervals, which is the type of motion we're trying to describe. So that by the time it gets to the final distance, d sub s here, it looks like it is really going very slowly, because the average velocity here between the 2 points obviously is a measured distance d final divided by the change in the run on the graph. So it does have a non-zero value, but we didn't go back to the garage, remember? The actual function of the motion is the blue line, and its slope is changing in time. The slope is very high at the beginning, and right there, a little past t final, can anyone tell me what the slope of that line appears to be? Does everybody still hear me?
The slope, where?
Above
Just the
the
slope of the
word.
green line?
Well, yes. Well, actually, the blue line. Above the word velocity, what would be the slope of that blue line at that point?
0.
You're right. So if I were to extend the green line to that point, the green line obviously does not have a slope of 0, and yet this blue line of displacement, and time is passing because that's how it was drawn, certainly has a 0 value. So we've got to interpret our motion a little more accurately or to the point, and that's a bit of a pun there. Okay, let's go to the next one. All right. There are problems with using average velocity. I don't know that I have to read this, but apparently there's some overlay here. So when we have an overlay like this, I'll try to read it the way it's supposed to be. There are problems with using average velocity, which when the motion is nonlinear, for example, circular motion, or when it occurs, circular motion paradox with average velocity occurs. When a race car goes around a circular track starting with an initial velocity of 100 miles an hour due east and returns to the same position after one lap, where the final exam is 100 miles per hour due east, then the average velocity is 0. And of course we discussed this at length, so I think you're beginning to maybe see what is happening here. A resolution to this problem when it occurs in nonlinear motion, 2-dimension, 3-dimension, circular motion, is to define a quantity called average speed. And notice the word here is changed from velocity to speed. Speed has no direction. When we're on a trip, we usually use speed, not average velocity, which is the distance traveled without direction divided by time. We use that more often than we use average velocity. We already know that something, excuse me, there's something wrong with average velocity. It doesn't match up at the end of the interval with regard to the slope and tangent at points. The slope between 2 points, of course. As useful as speed is, and that would be your speedometer reading, an average trip planning or an average at trip planning are, there is need to know both magnitude and direction for the motion. Just as the car trip was an ever-changing direction, particularly if your friend's house was along a winding road. This need for magnitude and direction to describe motion could be near to impossible to track unless magnitude and direction could be determined at an instant in time for each instant of the motion. This is a concept of tangential velocity. Notice it's got a larger font and it is in red. Obviously, there's something important about this. We're going to define, and notice the velocity sub inst implies it is a vector, it is instantaneous, which means occurring at a point in time, is the limit of the change in displacement divided by the change in time. As the change in time approaches zero, anybody remember that particular approach in calculus? Just say yes. Maybe?
Yep.
Yes. It's like a limit, right?
Oh, yeah. The first theorem of calculus deals with infinitesimally small changes in some variable with respect to time or distance or whatever. This statement should sound familiar. It's the first derivative of the displacement with respect to time. Here is the first difficulty with these very old PowerPoint. The vector v, instantaneous, is equal to the limit as delta t approaches zero. And there should be a delta d divided by a delta t. Graphical representation of this is as follows, and here are the 5 intervals of interest. We already know this first interval is a car that's going breakneck speed, but takes the foot off the accelerator so the computer can allow it to change its velocity in a parabolic manner, reach a velocity of 0, as someone reminded us. The slope of a horizontal line is 0. But we have traveled a distance, and at this point, it's as if I had driven out of my garage, took my foot off the accelerator, and I got to this point, and I realized, I'm at rest momentarily, that I forgot my textbook. So now this is one dimension, so I can't turn my car around in another dimension. But one way of looking at what happens here at this particular change in point is I can get out of my car, turn the car around, and that's laughable, but this is a model, get back in my car, and then begin to put my foot on the accelerator and keep it at some point, and come back to not quite my garage, which is over here at this D, but I get to this point right here, and I realize that my neighbor found my textbook on the ground near my mailbox. And she sees me coming back, so she stands next to my mailbox and holds the book out so I can grab it at this position. So I don't have to be accelerating in the negative direction. And notice, a negative deceleration is a positive increase in velocity. Now notice I've taken the foot off the accelerator. The car now is slowing down uniformly. And at this point it stops momentarily. I grab my textbook out of my neighbor's arms and I begin to accelerate because I'm late to class now. Accelerate, so I get on the interstate, and would anybody like to guess what is happening to the motion of my car along this straight line? Well, no. The slope of the line is constant, so it could either be my instantaneous at all points in time or my average velocity during the interval. In other words, I'm traveling with constant velocity. I am not accelerating.
I'm sorry. What was the question?
Yes?
What was the question that he answered?
He said it was increasing, and it's not. The velocity is constant. Ladies and gentlemen, I believe in lesson 2B, it explains all these motions verbally to give you some physical meaning of what is happening. we'll go over that briefly as a review of this, but the important point here, engineers, if you're going into the medical field, you've got to know where your equations and your definitions come from. And just as the graphs in Chapter 2 do that, they limit the number of intervals and what is happening. I have included all of the 5 possible kind of motion intervals in one dimension in this presentation. So be a little patient. We'll get to a thorough explanation of what is happening. Okay.
Professor, would
Now,
you mind going to the previous slide for just 1 second?
okay, you should have that available. So I'm going to move on.
Okay.
And if we still have that question, you can refer to the frame, and I can then write an answer, and that would probably be better. Okay. Next is the average velocity of each interval is drawn. Now, this is a rather primitive PowerPoint, and the interval from T1 to T2 should be the same line as T2 to T3. And I went over it with the green of our presentation today, and I didn't quite get the straight line, but and notice that there is, for each interval of the 5 kinds of motion, an average velocity from the beginning to the end of the interval that had the constant deceleration or the constant acceleration or the no acceleration value. This is true only because in the physical world that you engineers and medical folks are going to be spending your careers in must be polynomials, must have real solutions. If you have a function of any part of this, it should have at least one real root, or it's not the real world. Each interval here, if we knew the equation, and we'll be using equations a little later, should have at least one root. Being quadratic, I already know that if you have one real root, you're going to have 2. Would everybody agree with that?
No, because it might be an instantaneous point that it hits 0. Right?
I didn't hear your first part.
Even if it's quadratic, like maximum or minimum might touch 0, be 0. Right? Like the second derivative, if it's flat.
Well, we'll find that in the sample problem we're doing that you have to be a little more explicit. For instance, you'd have to say, are you discussing the maximum at a position or a maximum at a given time, which we will use functions in time. So you're really talking about when the value becomes 0 and at what time. We'll clarify that as we do an actual example this afternoon. All we have now is interpreting graphs. But also notice that each one of the average velocity secant lines would have, except maybe for this last interval where there is an acceleration of 0, will have some point that, well, could be considered a change in time interval. For instance, let me see what the overprint here. All right, it says let the time interval approach 0, then the green secant line backs into the red secant line in the first interval. We'd have, of course, a time variable function here would back into this, and then that one, which would have the same slope at that point. And then the same thing going on, and this is the example your book uses. To allow that back into a time equals 0, I think you'll notice that instead of being inside of the curve, it now jumps to a tangent line instead of secant, and that should be a familiar concept for you in calculus. The instantaneous velocity is defined as the slope of the tangent at the specific instant of time as determined above for the first section only, because each one of these sections is a different type of motion. This looks like the same parabola. This looks like the same parabola. This, of course, is constant in value. Okay, instantaneous velocity defined as the slope of the tangent line, determined above for the first interval. And what are we going to do with that now? Okay, here we go. Also might look at the fact that since we use polynomials that are bounded, that's the limitations in physics,
Professor?
we don't have motions that go to infinity. As engineers, we're not dealing with relativistic effects. We're dealing with cars and trains and bikes and snails and animals that are moving from one place to the other. So notice that there is a place somewhere in the tangent that would have these, that will have the same slope as the secant line or average velocity. That's because we're dealing with real values. And of course, of all the intervals. When the secant equaled the tangent, the acceleration was what? Acceleration right here is what? When the secant line...
I have a
Pardon?
question.
There's no acceleration at that point, right?
Thank you. Now, how about the question now?
What are the
Yes, sir.
physical? Yes, ma'am. What are the physical implications here between the tangent and the secant line? I don't. I'm just
Pure mathematics. Pure mathematics. Secant
No.
line is a matter of 2 points, and it's inside the curve. Notice when the curves are going down, secant line's up. It's a pure mathematical way of describing when you have a polynomial function that's limited, it has real values. It's mathematical. One reason why physics used it, it was mathematical. Sounds like I got a math major in here. Yeah.
I'm sorry. No, I'm definitely. I wish I
The
was.
tangent is the slope at a specific point, right?
All right. Well, what was the first words that you said?
I said the tangent line is the slope at the specific point.
Well, the better way to say that is the slope of the tangent line will be that instantaneous velocity that we're after. Oh, yes, we're after that. Thank you. That puts a cap on what I'm trying to say. Okay, here we go. Now, I think you will agree that this particular graph shows that there are tangent lines that have values greater than and less than the secant line. And in any interval, when that happens, we know then we have a solution both for the average and instantaneous. Instantaneous has one value because it's point-oriented, and the secant line tells us what the average value of thousands of tangent lines would be, of which we're not interested.
Oh, the secant between 2 points is the average of the tangents between those points.
Yes. Let me back up. In other words,
Oh,
if we
thank
can
you.
find that point right here on the previous slide
Yeah.
that has the same, then we can match them up. But we may not be interested in the average value. It only occurs once, assuming acceleration is either increasing or decreasing. Notice over here, they had the same value, second by second. However, we're interested in being able to look at the velocity all along the motion. In fact, if you plan to be a traffic engineer, you'll probably see a lot of curves like this generated and try to look at what's happening to the cars as they do a clover leaf or something.
So,
Okay. Yeah,
so the
then of course
secant will find the average between 2 points, and the tangent will find the slope at a specific point.
you got it. There's an excellent homework problem, and I forgot the number,
Cool.
that when you're doing it, you will need to know the fact that this gentleman has just quoted. And of course,
Right
this will conclude this lesson. I want to, I'm going to pull this down. I'm going to go to lesson 2B that will describe all 5 of these intervals, and I'll just go through them fast because you'll have a copy of that in your PowerPoint presentations. Okay.
Professor, what did the guy say that you said we would need to know?
Know that the slope of a tangent line is at a point, and that's instantaneous velocity. the secant between 2 points represents the average velocity in the interval.
Oh, what I
And of course, I'm sorry,
Oh.
we're not seeing one another, so I don't know if you're the same person, but thank you.
I'm sorry. Okay. No, I'm
That's
just
okay.
doing it. Thanks.
Okay, very good. While I'm downloading lesson 2B, you may want to take about a 10-minute break if you'd like, so that we won't be pressed for time. I don't know what your watch is saying, but my computer is saying about 2:12. Could we look at returning about 2:20, 2:22, and it gives everybody a break while I'm downloading the other PowerPoint?
Sounds good.
Okay. Good. All right. I'll get to you then. Yeah.
I found it. Yeah, thank you.
Oh, shoot. Hello? Am I still on? I thought so. Good. I thought I'd lost you. I accidentally touched my phone and it went bananas. Ooh. All right, what we got here? Get rid of this, get rid of this, get rid of this. Bingo. Ah, now I get full screen. No, well, I don't particularly want that. Here we go. There we go. Okay.
Professor, are you sending the video from your phone? How are you doing that?
No, I'm on a computer, but I have the PIN number that I give people if they have to go on the phone. I don't know why my microphone is not working on my son's computer. He's got 2 disk drives on this thing, and I don't know if one of them's controlling it or not. So, all right, here we go. Let's see what we can do. Yeah. Here we go. Add action.
Yeah, I want to do that. I want to I actually want to triple boot Windows, Linux Mint, and then Kali too, because I like learning about that stuff.
I'm at the present time downloading, hold that question until I get my, my added, action in. Come on. Yoo-hoo. There you go. Finally it clicked. Oh, come on. Cooperate. Woo. Oh, come on. Yoo-hoo. Hmm. I hope everybody is back by now. Can someone just say something and make sure we're live? Hello?
I can hear you.
Good. I hope everybody can see the screen. I think one reason why it takes so long is it is not really a PowerPoint. What they do is convert it to PDF file in order to put it on the screen, which is fine with me. I don't need a PowerPoint as long as it's static. As you can see, this is the first of 5 intervals, and it does talk about a car leaving a garage. It begins to slow down, and it slows down uniformly, so the acceleration is changing uniformly. It's constant, in other words, so the change in velocity is constant. The second interval talks about the fact that up here at T1, I momentarily stopped, then kind of turned on a dime and began to increase notice the slope of this line gets steeper and steeper, so the velocity is increasing as I return to the garage, but the direction is negative with respect to the change in velocity. It sounds like the acceleration is decreasing, but it's not. The minus sign is direction, not the fact that the acceleration is decreasing. One of the peculiarities of physics is you got to know what the signage is as well as the symbol. But quite obviously, looking at the tangent line here, that velocity is higher than it was 0 here. So it is indeed greater, but the direction is negative. Next thing, the interval where I have recognized that my neighbor was holding on to my textbook. So at this point, I took my foot off the accelerator, and now I am decelerating in the negative direction, going back from where I came. Remember, this is closer to my garage. Now here's where you have a negative direction and a negative acceleration value. So it looks like you have a positive acceleration. You have to be careful in equations when you have a negative and then you put a minus a, you end up with a positive. But if you draw a diagram with your motions, you'll know exactly what is happening, although the direction has been lost in the algebra of signage. And the last interval, as I'm accelerating to get back I'll get to college, I don't know if that looks a little steeper because I think I wanted to go faster. I was getting late now. And at this point, I'm on the freeway. I can put my cruise control on, and it will be a straight line. When the acceleration is 0, the average acceleration is equal to the average velocity. It's equal to 0 because the average and instantaneous velocities are the same line. You might want to use this particular lesson as a reference to our first 5 intervals and the discussion of the calculus that went with that. But now that we have looked at the curve here, let's go a little bit further with this curve. In other words, it tells you that the car decreased its velocity in the positive direction. There. Was at rest momentarily. Did increase, ending up with a velocity in the negative direction that had a greater magnitude. Decreased its velocity in the negative direction, which kind of looked like it was positive because of the mathematics. Increased its velocity in the positive direction and then traveled with a constant velocity. Acceleration measures how these velocities change in time, except for this interval right here. And the acceleration there was 0. And then, of course, the secant line matched the tangent line. And the average velocity equals the instantaneous at all points along that interval. It gives us a clue as to how to analyze this particular data. Using the discussion of average velocity as a reference, average acceleration, and this looks a little messy, which is delta V, which is equal. This delta should be over here in front of the V, with a line over it, which means it is a vector, divided by this delta should be in front of this I, and that would give it a unit of meters per second per second. Well, we abbreviate that, saying meters per second squared. Again, the average value of acceleration does not give instantaneous values, but motion in physics is divided into intervals of constant acceleration, where indeed the average acceleration will always equal the instantaneous. And that, of course, is confined intervals so that you can use equations that deal with constant acceleration. Instantaneous acceleration is the limit of the change in velocity over the change in time. And these symbols here should really match up, that should match up with this equation up here. In other words, this A value should be right there, equals dv over dt. Does anybody recognize that symbolism in the ratio to the right?
I do.
It is what?
You were saying
It is what?
something about.
All right, it was what? It is what? It is what? Watching my bouncing ball. What does dv with respect to time? Okay, we have just put calculus in our description of motion with limitations. Remember, it was a polynomial function. They look mostly at quadratics or straight lines. And they're closed. They're bounded. In other words, you can't have any kind of tangent function approaching an asymptotic line of some kind. Now, someone had a question. Question?
You were saying something about the average velocity and acceleration and like the implications of that. And I think it had to do with the top line. Could you just explain more about that, please?
Yeah, we can say that the average acceleration, and notice the average line, the vector line, equals that delta goes in front of that v, and that delta goes in front of that t.
Okay.
However, since we confine our studies in this chapter to constant accelerations, remember what happened to the average acceleration and the instantaneous when the acceleration was constant. Remember the straight line in the fifth interval.
Oh,
The
the average was 0 because the velocity was constant. So it wasn't.
You're right. Both the instantaneous acceleration and the average acceleration is 0.
Okay.
Yeah, and most books don't refer to that because they figure you can see it from the line. Well, I want you to realize that we're confining our study to constant acceleration. Okay, now I think we finished at least finding the first derivative of velocity with respect to time. Can anyone tell me from the distance as a function of time graph, that very first graph that I had, how can I find, if I can find the acceleration as the first derivative of velocity, how can I find the velocity using the function in displacement in time? If I called it function f,
by taking the interval of the acceleration.
You're right. In fact, the last section in Chapter 2 will do that kind of derivation. It's all right if you read it, but we will deal primarily with derivatives until we get to about Chapter 6, 7, and something like that, 7. So concentrate on derivatives, as my example problem at the end of these lessons would be. But if you want to verbalize it, if you have a function in time that represents distance or displacement, now why can I say both? Because they're straight lines. They're both in the x direction. Distance traveled, x direction, displacement, x direction. The first derivative of that time function will give you the velocity at that time, whatever time's given. If I have 2 points of time, I can find the average velocity, but that's not very good for us. if I know a time, then I take that first derivative, use my time value in it, and it will give me the first derivative of the distance function, which is the velocity. Then, if I take that first derivative, and if I take the derivative of the first derivative, obviously the second derivative, I now have the equation at the bottom of the page that we're looking at now. In other words, this is the second derivative of the function. V here was the first derivative of the function. We're also going to talk about maximizing those values, which somebody's already mentioned, but hold on to that for a minute. Let me now give you a few minutes, and I'm going to download the third portion of this lesson, so if you want to take another break, feel free. Let's see if we can get back on at about 2:45. Does that sound good?
Yes, ma'am. Yes, ma'am.
Okay, thank you.
Yeah.
Thank you. Very good, very good. All right, here we go. Okay. Mm. Oh. Um,
Professor,
Yes, ma'am.
my Wi-Fi/power looks like it's probably going to go out really soon. There's a severe thunderstorm right overhead. Are you able to record the remainder of this lecture in case I cut out?
What I might do is turn it off briefly and then it'll start up again. And I'm more likely to get it recorded according to our tech team. All right, this section is now being... Oh, nope. Let me see if I can get it off for a while.
All right, John said that he's recording the whole thing. Thank you, though. I just want to make sure that I don't miss anything. Thank you.
Yeah, well, yesterday when I talked to the tech team, I said my classes go for more than 60 minutes. And he said, well, if you can't get it recorded, and I already know that John Hartman said he'd do it, but at least shut it off, then start it back up in something less than 60 minutes. So if I do that, that might work. Might. Thank you for advising me, though.
Absolutely. Thank you for bearing with me.
This mode of learning is something else, but it will prove the mettle of those of you that want to be engineers or go into medicine. You'll find that in the workplace, patience sometime without blowing your cool is going to win the day. I'm old enough to know that. Okay. Oh, yes. Okay, yeah, I've got it off. I'll give it a few minutes before we start. Ooh, it's 2:45. Well, wait a minute. All right. No, it just continues the session. I'm not now being recorded. I hope I've got everybody back. I have already gone to a velocity as a function of time graph. However, there's something interesting here. We see in the first interval for the first 5 to 10 seconds, it appears velocity is increasing fairly uniformly. For every 2.5 seconds, another 2.5 seconds, you can see that we have the same slope value. And apparently the instantaneous velocity has come to 0, which means it had to instantaneously go from 4 meters per second to 0. And we do that stopping on a dime again. Actually, this is a separate function. This was a function in time. That's a function in time. And this is the same function in time. Whoops. Let's see, velocity in meters. What's wrong with that, folks? Hello? You got it. Occasionally, although I believe the 10th edition has corrected its graphic labels, at one time they intermittently would have problems with their labels. The discussion would have the right label and then the graph would not be labeled correctly. However, if you worked it with what the text said in the paragraph 4 portion, it would give you the correct answer. Same thing happened here. This is a meter per second or a meter per second squared. I don't know if I can do a little square. And then divide that by, oh my, a second. Now it's corrected. This same function now, you can go back and construct the distance as a function of time. Notice I didn't say displacement because I know displacement is the x direction, one-dimensional. Anybody have any idea how I could go back and use the information I have in this graph and go back and find the distance as a function of time graph? Actually, there's 2 answers to that. Anybody have any idea how I could go backwards and find my d as a function of time graph? It's not the same as our lessons 2A and B, because this is only 3 intervals of time. My lessons A and B were 5 intervals. How about if I knew the equation for this line? If I knew the equation for this line and I had a gentleman to hint at this, how could I get back to not a meter per second, but just a meter, which would be a function in distance?
Integration.
Anybody? You got it. Integrating the function here. We don't do that in physics because you'd let some kind of software do it. But if you're a computer person, you may have to write the software. But if you don't have the function, or if it were more complex, for instance, if the intersect was not at 0, so you could easily use the slope intercept here because the slope equals d. The actual area under the curve, would everybody agree? All of this. And then in fact, this is a single triangular function. So if I have 1/2 the base, which is 10, times the height, which is 4, 10 times 4, 10 seconds times 4 meters per second is going to give you 40 meters that you would have traversed in your distance as a function of time for the 10-second period of time. Kind of interesting because notice it accumulates. This is, hello? Oh.
We can hear you.
Yeah, I've got a telemarketer calling and it's spam, so I'm going to decline and I'll get back my phone. Oops.
Professor, I know you got years of wisdom behind you, but this is tried and true for my family, generations back. Do not pick up unknown numbers for any
You're
reason
right.
whatsoever, unless you are expecting a call from an unknown number.
Well, I help the older ladies, and they have to get used to that. Don't automatically pick up and answer your phone. I said, look at who it is. If you don't know, don't answer. Your friends know that they're probably on caller ID. Your friends will, if you think they're your friend and you don't identify them, just call them back, but don't redial.
They record your voice, and they can take even the minute inflections in your hello and create like more personable voice images from you. And it's scary. Be careful. It is fun to play. Yeah. But still, be careful.
Hello? Thank you. I have no idea. Considering it's working a lot better than yesterday, I don't guess I can complain since we're really communicating. I hope everybody saw my message in the upper right-hand corner. We were in how you could go from a velocity versus time back to a distance versus time, as long as we're in one dimension. That, believe it or not, because it requires the interval notation, and the book delays using the antiderivative or the interval notation until later in the course. But to challenge you, if you would like to do it, that would be fine. What I'd like to do is use what we got from the last lesson, namely that we can find instantaneous acceleration, and if we knew something about how velocity was changing in time, and we can pick that out of this graph. And so I've already done that. So using this equation that we have right here, which really becomes the backbone or the hinge pin of the equations of kinematic motion, which most of you may know from your general physics. If you ever wonder where they came from, what I have just circled, which is a result of graphic interpretation as well as a calculus derivative of functions, is the backbone of our four kinematic equations. And I'm using only this left graph because this is quadratic in time, which represents constant acceleration. For those of you that are curious as to whether or not the distance as a function of time would be cubic instead of just quadratic, this is a function where velocity, notice, is quadratic in time. And here is really a kind of how acceleration now is increasing with time and then decreasing. But this right here, this concept right here, is nowhere found in your text. This right here, whoops, it's not right. Oh, I know what I did.
Professor?
Yeah, this concept right here is just to expand your knowledge. Your text involves the physics of constant accelerations at this point. But if you're curious as to whether or not the displacement function is not quadratic, but say cubic, like some of your nuclear forces, if I have any chemists, it would look like this dark line. And you could also do the slope of the secant and tangent and go through the same logic, but you would be 1 degree higher in your description of motion. With that in mind, using this equation for the 3 intervals of time, we find if you substitute the initial value of velocity and then the time value, the final value, and then divide it by the time t, you should get this answer right. In other words, plus 0.4 meters per second. And notice the structure of a data table. The variable can stand for the actual variable. The time, obviously, is the variable, and of course, units and whatever. And then, since it was the same throughout the interval, instead of saying this for 0, 1, 2, 3, 4, 5, you can go ahead and say during the entire interval, that acceleration would be what's occurring, and that is represented by this line. Now, notice when the car was going at 4 meters per second, it instantaneously quit accelerating, which is the way we're going to look at this. Actually, it's mutually discontinuous. So I just identify the line where quickly its acceleration is 0. But this line can be misleading. The acceleration might be 0, but I am clocking greater distance in time. Notice my little bouncing ball there. I can add all of this distance in order to find out where I end up on a distance as a function of time graph. And then, of course, anywhere along the 3rd interval of time, I could take a slope value, which would be equal to the both secant and tangent, somewhere along here, all the way down there, or just a little bit of rise over run. Here's where the acceleration is negative. Obviously, from the graph, the slope is pointing from upper left to lower right. That would be a negative slope. So you may want to verify that you would end up with a negative 4 meters per second minus a plus 4 meters per second. That minus sign is the value down here, first minus sign. The second was the minus sign of the equation.
Professor
Question.
Kai.
Yes, question?
Thank you. Yes, ma'am. This A equals VF minus VI over TF minus TI. That would be the average acceleration, right?
Well, I have to put a qualifier on that. Remember, the acceleration here is constant, so it can be either instantaneous or average. You see how physics needs qualifiers sometimes.
Could you relate that equation to secant, like secant of velocity or something somehow?
No. Secant implies that I'm doing average value. This is
Right.
showing you more than that. This is showing you more than that because the acceleration is constant.
Right. I
It is
remember
applicable.
it was an average
Yeah.
of tangents, and I was just wondering, this is an average of something is, I imagine.
No, it's more than that. It is more than that. Don't give it a label. It is the acceleration during the interval is the best way to say it. Don't mention secant, don't mention average, don't mention instantaneous. Remember, the straight line when I got on the interstate had the same slope for secant and tangent. So the best thing to say is during the interval, the acceleration had a constant value of 0.4 meters per second squared. You see how tricky physics is?
So you're saying
You
there's
need-
really relate this equation to secant.
The slope
Well, you
is
know,
the same
if
at every
somebody would-
point.
Yeah,
So the
somebody would
secant
say-
would be equal to the tangent at every point.
bingo. Yeah.
What?
If somebody were to ask you to calculate the average acceleration, and you would see the portion of this line right here
Yeah.
is the same value. So you go, well, what's me about the secant value when acceleration is the acceleration is the acceleration, no matter how you determine either tangent line, and of course it overlaps the secant line.
Right. And I was trying to understand you used secant earlier. You said these are the secant lines, and it's just really been nagging at me because I just didn't understand how to relate it into it. And so I'm trying to tether that idea into this idea.
Okay, remember when we took the secant line and as the time interval decreased to almost 0, never got there. That's how we use the secant line or average values. We use average values when we travel and we plan a trip.
The secant line
But instead,
is the limit of the average velocity.
no. To take the slope. Take the slope and divide it by the time. There's no limit to the secant line. It is a line drawn. You only do limiting values when you talk about the tangent line. Now, when you allow the secant line's time interval to change, but your secant value is going to change, your average velocity is going to change. So you're really talking about how it changes, not just the average velocity. You're trying to put too much mathematics in the physics.
All right. I'm sorry. Is there any way I could find out more about this?
No, because they'll tell you it's math.
Yeah,
Let's
Khan
say you want
Academy, Calc 1.
Okay.
It's back in Calculus 1. In order to find a secant value, you must have 2 points. That's secant. That's average.
You've got 2 points here, right? F and I.
2 points on the curve. Now, if they ask for instantaneous, you can pick any point. If it happens to be a straight line, the 2 values are going to have the same answer. Let me give you a clue. I'm not interested in average anything. I'm interested in instantaneous. Does that help?
You said the secant
Well,
requires 2
It's
points.
because the average, the slope doesn't change. So the average slope is the slope.
So
Let him go back and let him go back and check. Let him go back to Calculus 1 and check the mathematics.
Yeah, the Khan Academy guy uses this as an example. So like,
Yeah.
do that.
I didn't hear you
Okay.
very clearly. Excuse me. One more time, Justin.
The Khan Academy guy, Calc 1, uses all this as an example.
Oh, all right.
He
Thanks.
explains the secant, tan, and all that.
Okay.
Gotcha. Now that we have the data table, and anytime you generate a graph for homework, please include a data table. I know that the solution key in the book and everything just gives you the graph. But if you realize that it's an interval like this, you can just say all points between 0 and about 10, little less than 10 seconds will have the same value. If you had same thing along any of this interval, the table for that, you don't have to spend a lot of time graphing because you will not be required to graph anything on my test. My tests are designed to do it now. Graphing is for calculus or algebra. We've mastered that. So
You said your tests were designed for what? I think you cut out.
my tests are designed to read graphs, not draw them.
Okay, thank you.
Yeah, drawing a graph is a waste of time here. If you become an engineer or an MD, you'll probably have a technician drawing the graphs or putting the data into your computer, and it will produce a graph for you. See my point?
Okay.
Yeah. I need to now go back to a whiteboard, and one of the things we're going to do is kind of do a summary. And I would normally have this also in a PowerPoint, but when they brought forth my PowerPoint, since they asked me to do this, they said they'd get them all. Well, they didn't. They did not get PowerPoint 2D. It's lost somewhere. So I will try to summarize what I had summarized there, starting by, if I can draw, some of you may want to find the kinematic equations listed in your text if you have your text beside you, or as I write them, as crude as it's going to appear, as we found out when I wrote phone up here, the fundamental equation for the development of kinematic equations with the condition that the acceleration is always constant comes out of this equation right here. And notice all of the discussion we had to go through to get to this equation. If the acceleration is changing, this would be a final minus initial. So the equation implies that the average equals the instantaneous. So I'm going to get off of this and go to the whiteboard. And so give me a few minutes to get there. Okay. Give me a minute. Look up the book. Okay. It might be in the summary at the end of chapter 2, but that's also, remember, they listed it somewhere in the body of the text. However, in fact, when we were talking about the kinematic equations derived from calculus, section 9, it is not required, but okay, your kinematic equations, well, on page 47 of your 10th edition is equation 213. Then they use the average value, but we're going to skip that. That has no acceleration in it, so it's a little misleading. Equation 213, 215, 216, and 217. Just to kind of give you an idea of the equations that can be generated from the equation we just derived using real life circumstances with respect to motion. And I'm going to have to get off of this and go to the whiteboard now. All right, now, you're welcome. Okay. Oh, we got it in there. Let me see if I can find this. Okay, whiteboard. All right, there we go. Nope. I want to get rid of that. No, I thought I had that song. So, all right, pause recording. Okay. All right, we're going to reset. Oh, let's see if I can find my whiteboard now. Okay. Okay. That was it. Got it? They're giving my whiteboard back. Thank you. Well, I got rid of that. Get rid of that. They gone. Come on. Didn't have a white phone. All right. Oh no. So, hello? Thank you. I had to reboot something and I still haven't got rid of something. Hopefully do that. The white screen doesn't come up, and I think it's because I have saved all of these things somewhere, but I will go to the big button at work. It's not. Well, I have already listed the 4 kinematic equations that come out of that last equation that we generated would be what I would want to write down. And you will notice that all of the motion homework questions as you're working would require your use of one or more of those equations. The best steps to go through is when you read the problem, try to draw a diagram with respect to what the problem means. And a good example of that would be the free fall that's talked about at the very back of the chapter after they talk about how you can analyze motion other than graphic interpretation. I think they have an example of a runner that's running, and then they talk about how to analyze your model of your motion, and that appears on page 30, 31, and then they go to modeling a runner as a particle, obviously, because we do center of mass. Then actually they derive the acceleration equation, which is 212, and then of course summarize the graphic interpretation. Slightly different graphic interpretation, but it contains almost all, well, 1, 2, 3, 4, 5 intervals that I did. There's also motion diagrams, which is not presented in your text, but a lot of standardized tests uses motions that are similar to figure 210 and ask students to interpret what it means. And you might want to read through that, particularly if you're getting ready for the MCAT. They will have motion diagrams like that as opposed to reading a graphic. They seem to think that medical people need to be able to see as opposed to what it is graphically. And then they have a discussion of how to derive the 4 kinematic equations.
May you please say that thing about the MCAT again?
The MCAT, believe it or not, uses motion not necessarily graphically, but by illustration, which is figure 210. Being a physics-oriented and engineering, they generally go to graphic. Of course, we spent all the lesson at this point in graphic. But if you are reviewing for the MCAT, you may want to look very carefully at figure 210. And realize when it's accelerating, decelerating, or it's moving with constant velocity. Those are the 3 major aspects of acceleration in one dimension. It's not too hard because if the cars are close together, and going further and further, obviously the velocity is increasing and you have acceleration. If it's slowing down, you have deceleration. Okay.
Okay, so that's how they denote it on the MCAT with those little circle things?
Little circle. Talking about figure 210?
Yes, ma'am.
Well, I see cars. I don't see circles. Page 37?
44. Ma'am?
I'm on page 37.
All right.
Of your text. But I tell you, I don't see this. Say that again, please.
You said this is what's going to be on the MCAT?
I said it's similar to what you may find on the MCAT. It depends on what version of the test they give you. It changes. Every test is different.
It doesn't look very threatening.
Pardon?
I said I know this is going to probably be wrong, but that doesn't look very threatening.
I didn't hear you. I think the weather is interfering.
Very threatening. This looks like a very simple diagram. The MCAT, everything I've heard about it is a crazy test. It's super complex over everything you've done and all your preparations, and my heart's racing.
You're right.
Just thinking about it.
Yeah. sometimes things are easier when you've had coursework that included the symbolism. And I think that may be one reason why they recommend this course, because there are many ways of symbolizing things, and don't try to memorize one way. They're trying to get you to think is what they're trying to do, and assimilate your information on the exam.
Okay.
And it helps to kind of have the experience. Yeah, that kind of thing. All right, good. All right. Until I can get the whiteboard, if you'll go to page 39, or if you don't have your text with you, if you'll just note that page 39 also has 5 equations. However, they have included the average velocity equation, which can be true if the acceleration is constant, and that could also be 0. Equation 213 we have generated graphically. And notice that there's only one acceleration, a sub x, because remember it was quadratic functions, and the second derivative is a constant then. So these equations only are applicable for constant acceleration. 214 makes the acceleration the same because you're talking about average with a constant acceleration. So it's a redundant equation. Your second kinematic equation shows you the change in position, but they have solved for the final position, and notice that equation really is a combination of the previous two. It can be arrived at using equation 13 and 14. The same can be, all you did was, in that particular equation, you solved for A and substituted, and then solved for X. In equation 216, notice you have eliminated the final velocity, let's say in equation 213, substituted in the second equation and solve that. The last kinematic equation is the last section in the text, which requires some integration of the function using, of course, bounded conditions, and that is going to be excluded from your study because it's really designed for your math majors or your physics majors. And according to most of, well, everybody's information page, no one has identified they're going to be a physics major yet, but I haven't looked at all of them. So if you're going to concentrate on sections 2.1 through 2.8, in fact, your homework is geared toward those two. There are some examples then into motion. I particularly like the one about the patrolman, that's example 213. It shows you how you can have accelerated motion related to some kind of motion that is maybe constant. I pretty much would do a problem very much similar to that, and you'll find its solution on page 41. Then I wanted to stop, and before I went into free-falling objects where the acceleration is constant, does anybody know the constant acceleration of a free-falling body? Freely falling body. If I were to drop a tennis ball, well, gravity is a force, and I'm after the acceleration. Yes, in other words, she was right. It is the acceleration due to gravity. But I wanted the actual results. The cause was gravity. If we're very near the surface of the Earth, your value is absolutely correct. In fact, I've been around the world, and in Nepal, the University of Kathmandu uses the international version of the Survey book. They are doing cooperative labs with Georgia Tech, and because they're almost a mile high there, just like the Air Force Academy, the acceleration due to gravity is only 9.79 or 78, and they have to use that in their laboratory work. But here in Florida, and the average acceleration due to gravity throughout the world is 9.8 meters per second squared. We will elaborate more on this acceleration value in Chapter 13, so it's a little less concerned with it at this particular point. In that case, the acceleration, when the ball is thrown vertically upward, the acceleration is downward at all times at the value of 9.8 meters per second squared is the magnitude, but the sign, by convention, will be negative. or minus 9.8 meters per second squared. However, when you throw the ball vertically upward, it is not in free fall until it leaves your hand with some kind of velocity, begins to move vertically upward, not even touching your hand. When the only force acting on it is gravity, it is in free fall. And of course, since the velocity is up or positive, and the acceleration is down at all times negative, it's going to decelerate or change its velocity to zero when it reaches its peak. The velocity at the top of that thrown ball is equal to zero. Can anyone tell me what the acceleration of that ball is at its peak? Thank you. No. Thank you for giving me that answer. It is wrong.
Wouldn't it be like
Remember-
-9.8?
Yes, remember that the cause of that value had nothing to do with the ball. It was the gravity of the earth, and it's still there. So if you were to draw a diagram of the motion variables, you would have no length for the velocity because it's zero at the peak, but you'd have a line. You'd have a line with an arrow representing the acceleration downward at all times. We will probably appreciate that better when we study projectile motion in the second third of chapter 4. But right now, you may want to look at, give me a minute, there's an illustration in the text. Excuse me.
Professor,
Yes.
realistically, wouldn't density and surface area and atmosphere...
Wait a minute. Wait. Let's concentrate on the lesson. We are in free fall, and I said the only force acting is gravity. There is no drag, no friction. That's what we mean by free fall. Nothing else is, yeah. So I set the limitations there, and the same thing in chapter 2. Remember, we're just doing accelerations of systems, and the acceleration has to be constant. And I know what you're referring to, terminal velocities and all that, but if you have friction or drag, the acceleration is not constant, and we're talking about constant accelerations here. Physics is tricky. You have to know your limitations and your restrictions.
You're saying
That's why they make a...
drag is not
That's-
constant?
What did I say? We're going to study that later. Study it later. Yeah. Oh, boy. If you're interested, it's the end of chapter 5. On page 43, they have an illustration of somebody at the top of a building throwing a projectile, looks like a ball, straight up in the air. Here's a case where you're throwing a ball vertically upward. You get to position B, tells you how many seconds it took to get you to position B. It tells you the Y value. It tells you the final velocity 0, and the acceleration at B is 9.8. In fact, at A, in free fall, that means when the ball left the person's hand, at A, B, C, D, and E, the acceleration in the Y direction is always minus 9.8 meters per second squared. And at E, that means the ball has just about hit the ground, but it's not there yet. It is still under the force of gravity, not the pushback of the earth. Interesting enough, if you don't have your book, look at page 43, and when the ball comes back down to position C, notice that it took exactly twice as much time to get back to C. It took half that time to get to the peak. It took another 2.04 seconds to get to position C. That means there was no drag. Nothing was holding it back going up. Nothing was holding it back coming down. Final velocity, though, is interesting. Notice that it is the negative direction of 20 meters per second. That means the way the acceleration increased the velocity by 9.8
Professor,
meters per
what
second.
graph are you looking at?
I'm looking at page 43 in your textbook.
Okay.
In fact, I'm just kind of reviewing it with you because I know when an example takes up the whole page, you probably, a page and a half, you probably know the example is critical. If you had thrown the ball vertically downward at position A or C, the velocity would be minus 20 meters per second because that would be what you would have thrown it at. You could have thrown it at minus 30, but I'm saying you throw it at minus 20. The acceleration is in the same direction, so the velocity will increase. At position D, it has gone up to 29 in the negative direction. Acceleration, of course, is still the same. And at position E, the final velocity without touching the ground is now minus 37.1 meters per second. Of course, the acceleration is still the same value. Now, I don't know what happened to my white screen, but I'm going to, let's see, resume recording. Let's hope that they, all right, because I would like to give you a function, and we're going to operate on that function. In fact, some of you, if you have a graphic calculator, you might want to put the function in the calculator, but you don't have to. Sometimes as an engineer, you don't have a calculator or a measuring device, and so you have to kind of think through something. So if you've got a pencil and paper, in fact, this might be better because I can't draw with this thing very well on the whiteboard. Let me see what this, no, that's restore. Does everybody have a piece of paper and pen or pencil? Can I give you more time?
I have a pen and paper. I'm good.
I'm good.
I'm good.
Okay. Anybody want to say, give me a minute? Anybody need a little extra time? This will be the last concept, and so we may have a Q&A period of time until 4:20 arrives. But usually, as I'm in the classroom, this exercise usually takes about a half hour. Okay, nobody stopped me, so, all right, this is a function in X. In other words, this equation represents motion along the X-axis, plus and minus. In mathematics, you use in mathematics,
Are you supposed to be seeing something on your screen?
Nope, the whiteboard did not come up. Yeah, it keeps giving me my old presentations. I don't know what the problem is. I didn't have the problem last week. So here we go. In mathematics, they'll call this a function in time. In physics, they'll just say X equals. So here we go. Here's your equations. Here's your equation. X equals coefficient 4, variable t to the third power, minus 2, variable t to the 2 power, plus 0 t to the 1 power, minus 10. That is a 4-term polynomial. If you want to put it in parentheses, it wouldn't be necessary because when you operate using calculus, you put aside or forgive units. And the reason for that is I've never seen the derivative of a meter before. Nobody has. But this, yes, actually that's a redundant placement, and the reason for the placement is so we can guarantee real roots. That goes back to the mathematics also. If you wanted to, yes, if you wanted to go back and put this expression in parentheses, make sure you put a meter on the outside, implying it's understood that it will be in meters. Your text problems, unless otherwise stated, your text, unless otherwise stated, will always use the MKS, or meter kilogram second, which is your metric system, not your engineering or British system at all, hardly. I don't think they even mention it. Now, my question to you is, what would be the equation for the instantaneous velocity? What would be the equation for the instantaneous velocity, which of course would be expressed in terms of t? Take a few minutes to see if you can get that. And then if someone would like to share their answer, you can be wrong. If you're wrong, then it gives me a reason to explain why, and that can be more important than just the right answer.
Professor, I don't know what we're writing.
You're writing an equation. Let me repeat it. X equals 4 t to the 3 power minus 2 t to the 2 power plus 0 t to the 1 power, which is a placement term, minus 10. Determine, using that function, the velocity as a function in time. Come on, use your calculus.
You just take the derivative, right?
Oh,
Absolutely. This lady is absolutely correct. And could someone else give me that first derivative?
12t squared minus 4t plus 1. Oh, plus
Well,
0.
actually, plus 0, right. A derivative of a constant is 0, and t to the 1 power really is t, but 0 times that is 0. So the derivative is only a 2-term value, and the gentleman and the lady was absolutely correct. Now, what would be the instantaneous velocity at t equals 0 seconds?
0?
Yes, ma'am. But wait a minute. Where would it be at time t equals 0? You have to go back to the original function. And all those t's are 0, which leaves how many meters? Where was it located when it started?
At 10? Negative 10?
Minus 10 meters, absolutely. Wow, we're progressing here. Now, of course, since I mentioned only one time, I was referring to the instantaneous velocity would be 0 when it is located at minus 10 meters. Well, how about the acceleration at that time? Well, I'd be interested in instantaneous. How can I find the instantaneous acceleration if I use the instantaneous velocity equation that the lady and gentleman gave me? And they were correct. How can I find the instantaneous equation for acceleration? Or just the acceleration? Remember the equation we generated?
Take the derivative
Yes,
again.
you take of the displacement, or the first derivative of the velocity, is two different ways of saying the same thing. And would somebody volunteer the answer that has not given me an answer yet?
14t minus 4.
Okay,
24.
look at
24.
she.
24t.
You got it.
Minus 4.
T minus 4. Now that we have the instantaneous, well, it can be the instantaneous value if I had a single time. I'm going to give you a single time, which makes the use of that time at a point the instantaneous acceleration. At t equals 0, when it was found that the velocity was 0 and the displacement was minus 10, what is the acceleration at t equals 0? And that will be instantaneous because that is one time. It is an instant in time.
Negative 4. Negative 4.
Minus 4 meters per second squared. Here is a case like the free fall, where the velocity can be 0 and the acceleration non-zero. which means the acceleration must be a change in velocity over time, not just one divided by the other. Now, I have two questions that your book has in homework, but they failed to give you some examples for. Now, with the displacement function, with the x function, with your v function, and with your a function, here's the question. Remember, ladies and gentlemen, I've made out your test already. So it's early warning. Okay. What would be the time when this particle, whatever it is, reaches its maximum displacement? What time would it be, single point in time, when the object has reached its maximum displacement? Does anybody know what condition of the variables that we have here when you have maximum displacement? Now,
You're going to take the second derivative.
The limit to
Zero.
infinity?
okay. Actually, ladies and gentlemen, at this point, erase that. At this point, usually the entire class is, what did you say? When the object has reached its maximum displacement, which means as far as it's gone while it was moving, and the moving is represented by v. So another way of asking this question about when the displacement has been maximized is to say the velocity has reached 0. Now, wait a minute. It was 0 at time t equals 0. So the question here begs that the time be somewhere after t equals 0. Would everybody agree? So set your...
Asking for the maximum displacement, or, right?
That's it. Yeah, which means to... This is a little like the second derivative test, but you're going to use the first derivative. Set your first derivative equal to 0. That is saying that your velocity is 0 when you solve that equation. For t equals 0 is a redundant answer. So take your first derivative, which is v, set it equal to 0. You will get the following equation. 12t squared minus 4 equals 0. Solve that for t, and of course most of you realize that one of the t's is the t equals 0. Factor 4t out of that expression and you get what?
T plus 2 and t minus 2?
Well, we want the time, no, we want the time, yeah, we want the time positive, not negative in time.
Get 1/3.
2?
Yes, the lady is correct.
Equals
Nope,
1/3.
nope. You will get, all right, okay. If you factored 4t out, you
Wouldn't it
would
be
have
1/6?
No, it's 1/3. Okay, let's go back. Let's don't do any factoring then. Let's just take t out. You'll have t equals 12t minus 4. The t that's been factored out is the value for t equals 0. That's redundant. We want a time beyond that. All right, now let's take that 12t minus 4 binomial and solve it for t. What do you get?
12t, you mean
4.
24t minus 4?
You'll get 4 divided by 12 equals t. And that equals exactly what the gentleman said, 1/3.
No, I didn't say that. Ashley said that.
Hey, I don't know who I'm talking to. Don't waste my time now. Come on.
I don't understand how she got 1/3 though.
All right, that is algebra. Review your algebra and your binomial. You need to review how you solve equations.
Well, I don't.
Now
Wouldn't it
Yeah,
be the
now-
square root of 1/3? Because you...
no, No, we factored a t out of it. Review your algebra.
Oh, okay.
Let's go back and look at how we're going to use that 1/3 of a second.
That's the problem. I don't think I have enough of the problem like written down. I don't think I'm on board. Yeah. Oh. How does this
Thank
give
you.
us-
That,
how does
Thank
this
you.
maximum Thank you very much. But how does this give us the maximum displacement?
all right, now. Yep. Well, you find the time where it has maximized its distance. Now you take that 1/3 second and put it back in your displacement function. In other words, 4 times 1/3 to the third minus 2 parentheses 1/3 raised to the 2 and then minus 10 meters. I'm less interested in that method because that is a pure substitution, to be frank with you, and is really algebra. It's not physics. It's not even calculus. It's the results of using a maximizing first derivative test. Now, what about what value would the acceleration have when you're at this maximum displacement? What would the acceleration be at t equals 1/3 of a second is another way of asking the same question. Can anyone tell me the first step or the equation you want to use to find the value of the acceleration at t equals 1/3 a second?
You would plug it into the 24t minus 4.
You mean the 24t minus 4? Yes, ma'am.
Yep.
And what would you get for the, what would you get for the acceleration?
4.
Minus 4. Well, no, you're back.
Positive 4, right?
Yeah, positive 4, thank you. Trying to avoid redundant answers, but I wrote this function to verify a few things that I'm going through. Not every function is going to have a cubic function because that implies the acceleration is not constant, and we've just been studying constants. You've got homework problems though that uses t to the third, so I did.
Can I ask a question?
Sure.
You said for the maximum displacement, we took the first equation, or we used this derivative and then set equal to 0.
Well,
and then
you mean the first derivative of the function.
Right. And then
Okay, good.
you plug number 1/3 into the original equation?
No, the 1/3 was the result of equating the first derivative to 0.
Right, but I
It's
thought you said you were plugging, before you were talking about acceleration, I thought you said you were plugging it into the 4t cubed minus 2t squared.
That's because I want to know the displacement. There's a difference between time and displacement. Remember,
Okay,
we set the first derivative or velocity equal to 0 when we were maximizing the displacement. And the time it takes to maximize that displacement solving that first derivative set equal to 0 gave us t equals 1/3 second.
Professor, can I please ask a question?
Pardon?
Can I please ask a question?
Yes, go ahead.
Thank you. This, I don't know if this is on an interval, but why 4t cubed is the largest power of t, and that's positive and always increasing. And so this function must always...
Wait a minute. You're talking mathematics. I'm talking the use of a function. Let's just say the function as given, which means no discussion. The function is 4t cubed minus 2t squared minus 10. And if we want to know where it's located for any time, it just happens to be the time where v equals 0, I don't like that question because it's algebra. I like the question about what time will the maximum displacement occur. I don't care what the maximum displacement is. I just want to know where is it in time, and it's 1/3 second.
Okay, thank
That's
you.
all. Yeah. If you want to know the displacement, just substitute it. That's algebra.
Professor,
Now-
I'm asking you a very detailed question, clearly tethering this to physics. I don't understand. Can you please try to help me understand? I know this isn't basic algebra because I aced basic algebra and then I tested out of it and I tested out of it again. and
Oh,
then I
wait a
realized I
minute.
couldn't
Calm
even have it.
down. Calm down. To know something and to be able to apply it are just not the same thing. They're related.
I'm asking you for help applying this. Can you please help me?
Well, first of all, accept the function.
I
Okay?
never
Take the
repeated
first
function.
derivative.
I'm trying to work with the
Okay.
function.
Take-
Just,
Take the first derivative of the function,
I know.
which I think everybody did.
How are
Okay,
you gonna
now-
answer the question if you don't
Now,
hear it?
how do we want to use the first derivative? Well, I want to use it by determining where in time the maximum displacement occurred. Now, that means I want to solve
The first
the
derivative.
first derivative. I want to solve the first derivative for time when I set the velocity to where it quits changing the direction, and that would be when v equals 0.
You want to find when the velocity stops changing direction.
Well, when it comes to 0.
I am so sorry. Thank you. Why?
Just set
That's just to find
the
the
first
local
derivative. Wait a
So
minute. Set the first derivative equal to 0. That's what that means in calculus.
Right.
To maximize, it's called the second derivative test, but this is the application of that derivative. To maximize the next higher function, you take the derivative and set it equal to 0. In this case, it's the first derivative set equal to 0. Solving for that, I believe everybody now agrees, is 1/3 of a second. 1/3 of a second will tell you where the displacement has been maximized,
I understand.
which means, yeah,
I-
which, you know, like my car went up, and then it turned and went back toward my garage, and then it went back. This is where I was at the place where I first came to rest to turn my car around, if you can put it in graphics of your mind.
So you're not
Now
finding
that I've got,
the maximum of the equation, you're just finding the local maximum that's,
well, you're finding it at the first time after t equals 0.
all right. Okay.
Yeah. I'm not going to ask for 2 or 3 more maximums and minimums. We're after the first time after t equals 0. We just don't have the time to do all the calculus. Yeah. Now that we kind of hashed that through, now I think we've already taken the second derivative, and we can take the second derivative and set it equal to 0, and we would be maximizing what then? That's your second derivative test. That calculus teaches you
Your
that.
acceleration.
Take 24t minus 4 to maximize your velocity. You want to set that equal to 0. And that's where the acceleration quit. Now remember, the acceleration here is not constant. It's a cubic function. So it will be equal to 0, whereas before it was equal to like 4. That's why I use a cubic function, so we have something to deal with here. Take your second derivative, set it equal to 0, and that maximizes the velocity. Where is the velocity maximized? Let's solve that equation. 24t minus 4 equals 0. T equals 1/6. Now, what would be the value of the velocity at that time? In other words, it's been maximized or minimized. It's still the slope of the line changing direction, top of the parabola, that kind of thing. Take the 1/6 value and place it in the velocity function. What value did you get when the time in that first derivative, the second equation of motion, that would be the first derivative? You got what?
Negative 1/3.
Absolutely. In fact, generally, tests and homework will not have fractions. So on a test, you'd probably see minus 0.33333 and meters per second. I might also on a test have a plus 0.33 meters per second to see if you were at least sign conscious. That would be where you've reached maximum velocity. Or maximum, that would be where the velocity's value when the acceleration was equal to 0. Yeah, I got it said finally. There are some examples of this, not all of this, in your homework. And if you're working on it this weekend, let me remind you, except for Sundays, I'm available 10 to 10, except on Monday and Wednesdays, and I have a second class after this one. I usually have dinner between the classes, and I won't be free until about 9 o'clock. But if you still have a question, obviously I'm still awake until 10 o'clock on Tuesday and Thursday evenings. So we could run through the function they give you. This chapter, however, will concentrate on just quadratic functions. So if I were to take the second derivative of a quadratic function, could anyone tell me what I might get out of that? Generally? For instance, if your function was only the minus 2t squared minus 10, after you've taken the second derivative, somebody want to do that real quick? What do you get? In other words, you get a constant value. After two derivatives and you had a quadratic term, you're going to get a constant value. There is a very specific homework problem that gives you only a quadratic function, and anticipate that when they ask you to determine acceleration, it will be a constant, no variable t involved, as your answers would imply. So I have worked through a problem that does have non-uniform acceleration or a changing acceleration. I've gone through the same example that shows you where the velocity may be equal to 0, but the acceleration is not. From the discussion of free fall, we also saw at the peak that the velocity was 0, but the acceleration was constant, 9.8. There's some interesting examples of that throughout the text. In fact, I may not have assigned them all. If you would like, I'll try to come up with some more examples. I can go through all my old tests and see the examples that I've used in the past. That won't be too hard for me. But considering the time I gave the analysis of this cubic function, I hope you can come to the conclusion that I at least have one or more problems associated with this kind of work. Does anyone have a comment about that? Yes,
I
ma'am?
would appreciate as many examples that you could send out as possible. The more practice, the better we get.
Me too.
You're right. And I try to avoid the deliberate examples of your text because they're there for you. In other words, my presentations are not designed to replace the text in any way. It's designed to augment, to explain, to broaden your understanding, particularly with regard to application. I think I mentioned the MCAT sometimes does a little car thing, which the physics qualifying exam won't do that, or our achievement test. They'll go more to equations like we've been dealing with. So I just kind of augment it. I'm trying to also get a sample test put together for you, particularly multiple choice format. It may take me a little while, but we don't have our first test until what, 2 weeks from 2.5 weeks, covering chapters 1 through 5, and we're only in chapter 2 now, so we've got a while to go. Looks like I have about 22 minutes left. Let's go through any general questions you might still have.
Can you go over question 36 from the homework, specifically part B to that?
Is that chapter 1?
Yes, ma'am.
Yeah, give me a minute. Let me see if I can find my folder. Yes. And what problem was that?
Question 36, part B.
Oh, okay. Problem 36. Okay, 36. Okay. Use a calculator to find the largest angle which tangent of alpha may be approximated by alpha with an error less than 10%. Actually, the purpose of this question is to realize that small angle approximations sometimes are used, particularly toward the end of your study with simple harmonic motion. It says demonstrate that for small angles less than 20 degrees. Okay, I would suggest you use 5 degrees, let's say 10 degrees, 15, and 20. For all of those degrees, or maybe just for 10 and 20, that's all. Find the angle of 10 degrees in radians. Do you know how to transfer degrees to radians? There are 2 pi radians.
Yes, ma'am.
And 360 degrees. Yeah, and 360 degrees. Okay. So take the tangent of that value in radians. You have a calculator that will go to radians. Then also take the sine of that angle in radians. In fact, if that angle is less than about 5 degrees, to 3 or 4 decimal places, the sine of that angle in radians is approximately equal to the tangent, which is a small angle approximation. And so it will also be equal to about the number of radians you have. And of course then the pi, and then we were talking about what, using 10 degrees divided by 180 degrees.
Okay.
The purpose,
Part B of that question.
yeah. I'm really interested in a little bit of notation, following a notation, seeing how good your trig is. If you've been introduced to small angle approximations, am I going to put that on a test? That's a very good question. No. It's more a trig question than a physics question. It may enable you to do simple harmonic motion, circular motion when we get to that, but it was merely meant to be a little like a review. I appreciate you asking because a lot of students might not have been aware of the small angle approximation. Excuse me. Okay. All righty. I don't know if any of you have had a chance to look at the online virtual lab sections. I am looking at getting some references. I've already referenced your labs to chapters, and a lot of those labs really have things from more than one chapter. But if I can find a real live lab that we may have been doing, maybe in the classroom, I'll use it as reference because I find that they do very little theory discussion in these virtual labs. And I try to have them done after we have studied the content. Many of them will have a video on how to do the virtual lab, and will have more than one part, maybe saying how you should manipulate the variables. Keep all of the initial answers, but only change one variable, that kind of thing. And so I have picked not all of the parts, sometimes only parts 1, 2, sometimes only part 1, 2, and 3, and sometimes there's no direction at all. And when you have no video showing the direction and how to do things, what I'd like for you to do is, by trial and error, give a critique to that virtual lab. Because in doing that, and you'll probably see how it relates to the chapter that it comes after, and the one particular one that I'm thinking about is projectile motion, is really more like looking at what happens when you throw something at an angle off the top of the building, what happens. But by the time we get to chapter 4, we'll have some equations that you could use that would help validate why it was doing what it was on the screen. And then instead of doing an analysis of the lab, I would do a critique of the lab as presented, because I have some ideas about maybe how they ought to change it to a true cause-effect lab.
Professor,
Yes.
And this seems pointedly elementary, but it doesn't go over how to calculate the error for this expression in chapter 1, I don't think.
All right. Yes. Well, the state of Florida mandated that the uncertainty of a function be included somewhere in your education. Now, I have gone through almost every virtual lab that's available through Boston University, University of Colorado, and the physics aviary. And they, because it is so time-consuming to look at the uncertainty, have not used it. However, in the Physics 2 course, when they get into resistant effects, they have what they call tolerance, 5, 10, 20%, which is an uncertainty measurement. In that course online is where we will cover the state mandate. So any test items, I avoided homework questions that ask for percent errors or uncertainties. In fact, if there's one embedded, just skip it, because I must.
Oh, okay, thank you.
Yeah, I took out that. It's, you know, especially since, well, even if I got to my whiteboard, I can see me trying to write those equations. I got to figure out a way to do that. Obviously, maybe even on a PowerPoint. And they did not have my 1D presentation, which includes samples. So your book though has samples of free fall. So we got equation application done through free fall in that example. Okay. So forget uncertainty, forget tolerance. If you encounter one, just ignore it.
Just to clarify, you're saying that this should have been covered earlier in our education, and if it wasn't, then it just doesn't matter because we're not using it, because nobody uses it till next class?
Well, actually, I'll tell you where that came from, because when I was at Florida, and you know it was 53 years ago, we didn't do things like that in physics. And then the engineering department said, you're training our engineers and you're not telling them that there is no measurement that is exact. In fact, in the quiz today, the way I asked the question about what percentage of grade is evaluation, there could be 1, 2, 3, 5, 6 different answers. The reason is, how many decimal places did you take out all of the percents? Did you include, say, quizzes? Did you include the final exam? That answer is conditional, in my opinion, because an engineer would ask, what do you mean about percent of the building of the bridge? You know, how far can we be up? Yeah. So you can almost put almost anything as the percent of evaluation, as long as it wasn't 100%. Because virtual labs are not really evaluation, they're performance.
Hold on. Actually, I wrote in my email, I said all forms of these grades is some form of testing your knowledge. And so it's like, depending on your definition of testing, technically everything we get graded for in a class is testing of some sort.
Because you qualified it, young man, you get the total point. You see what I mean?
Okay.
And that happens in engineering. All right, it happens in medicine because you have to know the individual. You can have two individuals with the same presentation, and the diagnosis is different because of circumstances of the person or something. It's like this virus going on. To some ages, it exacerbates itself. In others, if your immune system is challenged, you can go on and on and on. So you have to be careful. Did you notice that through the presentation, excuse me, this afternoon, let me get a drink of water real quick. If you notice, during the presentation this evening, I qualified. I talked about limitations. I talked about peculiar things happening when you get a negative acceleration. It looks like you got a positive acceleration. One reason why a lot of people cannot master this stuff is they want it direct, single, only one answer. Okay, engineers, you're never going to have one answer. First of all, you'll never work in a single group. You'll be in a group of people, industrial, electrical, structure, you name it. You're going to have to learn to live with one another. That's why I think this online teaches us patience. Notice how everybody's polite and give yourself a chance to ask the question. This is a very valuable skill, both in medicine, both in experimentation, both in performance, like your engineering fields, and computer science. My husband was a systems analyst, and sometimes just shutting up and listening, and then maybe go home and think over it, because you're going to be in a profession. You're going to have a salary. It's not a wage earner. It's not hour. As a professional, you will be thinking 24/7. When I worked with the electronics firm in Wayne, New Jersey, while my husband was up there with IBM and Prudential, and the one thing they did is we had a brainstorming session at the end of the week on Friday. And we tried to come up with something we wanted to think about that weekend to help solve a problem so we could go home by 5. But there were a few Fridays, and I called my husband and I said, have pizza. We're having a snafu here. Or Interstate 80 up there was blocked or something. I'm being paid to think 24/7 about limitations, how best to do something, whether or not this counts for this course. And we just went through uncertainty. It doesn't. And I cannot emphasize the people in this class, I think you're aware of it because you're applying it. Just like the gentleman that says, well, wait a minute here. Isn't the whole course evaluating something to a lesser or greater degree? But I would be the first to admit virtual labs it's a tough call unless you have parts 1, 2, and 3 and you're changing only one variable and you can conclude the right thing. And the homework, of course, is application, but I hope you're learning, and I hope you keep your notes for your homework so it will assist you in testing. I hate to give you a huge lecture here at the end, but are there any more questions?
Yes, Professor, just to be clear, 36B, as with other questions that have to do with error and that sort of thing, should just be forfeited because they have to do with error. So we should just not do 36B and other questions like that. Correct?
Actually, since it was really a review of trig, and I know that we're only going to use it with the simple harmonic oscillator. You could probably forego that completely. The 1 or 2 points it's worth is not going to fail you if you can look at it like that.
Yeah, you went over 36A. There was a second part that was like the 10% difference between the tan and sine of the radian.
Yeah, as you talk, I'm getting a little resonating. Maybe you're near a wall, so I'm getting a slight echo from you.
36B, it's you went over 36A, but he said that you didn't go over 36B. It's got the error with the 10%, and we don't know whether to do that or not because we didn't go over it.
She kind of started to go over it, though, if you were actually paying attention to it, because she was telling you to convert it into radians and then find that tangent. And then all you have to do to find the percent is take that tangent minus the original or minus the original one, divided by the one that you just got, and multiply it by 100. And then you get the percent.
The lady's absolutely right, because remember that's a review problem as to how to manage small angles and your trig, and some of you may not have had that background. However, if that lady will remind me in your homework that you just explained what I taught you, I will give you extra homework points because you got the message. Thank you, ma'am.
Ashley,
So what would
if
you
I-
like me to do, ma'am?
Tell me that you're the one that explained the part to the class again.
Okay, so what I did, I got help with this one. I just couldn't quite fully understand it, and then you helped me get it to where like the light bulb
Not a problem.
actually clicked.
That means
so
you're using your resource. Yeah, you're using your resource material.
Yes.
That's one of my objectives. Learn to use. Uh-oh, I've got lightning. That's okay. I don't think I'm still live, right?
Yes, ma'am.
Hello? Okay. Phew. All right. Next question.
So I just wanted to, if it's okay, just explain really quick part B, because it's actually not hard once you understand what you're supposed to do.
Yeah. The main thing is use alpha and radians.
Mm-hmm.
And if you use real small angles like 1 degree, the tangent of that angle in radians has the same sign of the angle in degrees, which has the same, I think, yeah, which has the same 3 decimals as the degree measurement.
Yeah.
Yeah.
Really off by like
Oh,
1,000.
that's right. And sometimes they use small angle approximations, and we don't use it directly in this course, but the next course we'll use it in chapters 36 and 37. It's one reason why it's kind of a review problem. But when you're using, say, a pendulum or a simple harmonic oscillator, and you only displace it about 1 or 2 degrees, and you can only take rise over run measurements, you want to use the tangent as opposed to the sine is really what they're getting at.
Mm-hmm.
And engineers are more concerned with, engineers are concerned with how can I take that measurement, although I can't get to this particular side. If it's small enough, I can use the tangent instead of the sine, that kind of thing.
Yeah, and I do just want to mention for part B, you kind of have to ignore the less than 20 degrees because you're going over that. Like once you get to 20 degrees, you'll realize that your percent is 4.09. But once you get to 30, you're getting closer and closer to that 10% error.
That's right. In fact, you just learned this. If you're getting near 30 degrees, you're going to have to make considerations for other side effects that's measured. And I guess the best way to look at that is when we get over to the vertical circle in chapter 6, we might elaborate on this a little more. But that's in chapter 6.
How do you get the percentage?
Have you ever taken a percent error?
I guess we just do the difference between the tan and the sine of, I guess, an arbitrary radians.
Yep.
So it's saying that the difference will be apparent just by converting the units?
You got it.
Oh,
Thank you.
okay.
Yeah, you see again how this problem is a review.
How can I learn that, John? Where? I honestly don't
Madison.
remember about that.
Madison, can you hear me?
Yeah.
If you go onto your MyFSCJ account, there's an awesome resource called BrainFuse. It's online tutoring and it's included in your tuition with FSCJ. You will be connected to a live tutor, an actual person who can walk you step by step through questions that you're struggling with, okay?
All right. Thank you.
That's for all of your classes, coding classes, mathematics, science, history, English, every single class they have a tutor for.
Okay, let me ask you a question.
Sorry
Have you
for-
tried to Yeah, have you tried to use a computer for physics or calculus yet?
Yes, ma'am.
Wow, did it involve calculus? The question you had, did it involve calculus?
Yes, ma'am. I've
Not
done
yet.
AI before.
Okay, did they help you?
And stuff with matrices.
Did they help you solve it?
Who?
When you went online to do the tutoring?
I've
No,
gotten a lot of help with online tutoring with my Calculus 1 class, and they've
Uh-huh.
helped me a lot there.
Okay. My students in the past have found that sometimes they have difficulty applying the calculus to the physics. Sometimes they'll go back and graph the function and go through how I use graphing to get to the calculus. I really don't mind which way they go as long as they can help you. But I think you realize that at the end discussion, the best way is to take the first derivative and operate on it, take the second derivative instead of trying to find the area under the curve and all that. But they certainly have a viable method, ladies and gentlemen. They can certainly help. And I believe in resource usage. When you get into the workforce, you'll spend a lot of your time researching things based on the project you're given on the internet. You'll all be given a topic, and sometimes there's hundreds of feeds, particularly in engineering. And then you come together and put it all together, whatever you're solving, building a bridge on a certain type of bedrock, you name it. And some companies decide that whoever presented the program, then resources, will get a subcontract to help work with you. When you're doing that, you're learning a very valuable skill. That's why I talk about use of resources.
How do you, what opportunities are you talking about?
Almost any field in engineering and medicine, you'll never be working alone. If you have a project or a patient that is hard to diagnose, you're going to seek resources and people, sometimes your senior engineers, sometimes a subcontractor. And the reason you want to do that is if something goes wrong with your project, after it's been completed and paid for and you get sued, then you have subcontractors that will share the blame, I guess, is a way of looking at it. It's done all the time. And that is a matter of resource utilization. In other words, ladies and gentlemen, we're not in these careers to be a sole person. We've got to learn to live with one another, work with one another, give time to think, because your employer is going to expect you to think 24/7. I'm sure some of you have probably experienced working a calculus problem and you just couldn't solve it, so you went ahead and went to bed, got a pretty good night's sleep, and did any of you wake up and have a better idea as to how to do the problem and maybe solve it?
Yeah.
Yes, that's a little scary, but that's what's happening. And in a profession, you're paid to do that. So if it's already happened to you, utilize that time that your brain will be free of physical things and just sleeping, and it will sit there. And most of you know the psychologists will tell you your brain is sorting through everything you did that day. And when it gets to that problem you didn't solve, it's probably going to sit there and stew on it a while. And it may indeed give you some insight the very next morning. I have a lot of engineer friends that have pencil and paper by their bedstand so that when they wake up, if they get an idea, they write it down immediately.
There was
Actually, if you tell me,
a famous physicist that used to sleep, like he would take naps with a ball in his hand, and this way, as soon as he would like fall asleep, he'd drop the ball, wake up, and be able to finish the problem.
Yes, I know there was, what's his name? more than one scientist did it. Watson, that worked on the DNA, did something similar to that. He would go and take about a 15-minute nap, come back, and he'd have an idea.
Mm-hmm.
I don't know if he did the ball thing, but oh yes, I agree with it. I agree with you totally. Okay, any other questions?
I have a question about the labs.
Yes.
we go to that website and then just search for like the #1 lab, which is the PhotoGate Acceleration Pre-Lab. So we'll have to go to
Yes,
the
and
website.
it's going to be, you have to scroll down until you get to, what is it, determining acceleration using PhotoGate timers, which you'll need to do for your Newton's Law lab, which is very much like a lab we would have done in class anyway. And the Newton's Law lab is very much like a lab we would have done in class. And I'll feed you those labs. I don't have them in there yet. But those,
Okay.
the way they manipulate.
You will be
ahead.
putting them onto Canvas so we can access them straight from Canvas?
No, unfortunately, Canvas does not have a live link because it doesn't show up in blue. And I think the reason is they have a top secure pins and codes or whatever, as explained to me. So you have to get out of Canvas and go to the Physics Aviary. And as soon as you click on it, it will give you an introduction page. Somebody's holding a spring or something. It's very interesting reading what that page says, because if you read that introduction page to the Physics Aviary, it's going to sound a little like what I was just talking about. And that is, if I can share a resource with you so that you can share it with another and another and another, look at the impact we would have on the world. It's very interesting reading. And people for, I think, the last 17 years have been feeding virtual labs. Some are like games, and I don't try to assign this. Others are cause-effect. Some are a little longer than others. I would hope that you'd try to devote about 3 hours per virtual lab, because really half of the week is your lab time. Just do what you can in the due date. And there's nothing to prevent you from working on the labs before they're due, a month before they're due. It depends on where your time is available. You could turn it in early if you wanted, or wait and turn it in to see if you had any feedback before you turn it in. Again, a part of how you're going to spend your time, when we have a lab day, we'll have a quiz over the last conference we had. Then we'll have you will be released from your conference to go and do your virtual labs. If for some reason you can't do it that night, it's really none of my business. I know that you would have done it maybe on the weekend and certainly would meet the deadline. Does that help a little bit?
Yes.
Okay.
Yeah.
And in fact, I am going to be on the computer, and I'll probably stay in the conference the night of a lab in case somebody does the lab during class period and runs across problems. Because for the last semester I used 4 of those virtual labs, and the students gave me feedback for them. In fact, I dropped one. We don't like it. And I will be available until 8:50 to assist you if you are doing your virtual lab. And
Okay,
remember, I said I will. Yeah, I will always be.
So from the calendar, it says that.
We should be coming up in a lab in about a week and a half. 2 weeks. Today's Thursday.
It says
Yeah.
on this calendar that on the 4th, which is a week from today, that lab 1 required. So does that mean we'll be doing the lab on next Thursday in class, or it has to be done? Let's back up. You will have a quiz that day that will cover Chapter 3 and part of Chapter 4. That'll take maybe 15 to a half hour. Then as soon as you finish the quiz, you don't even have to tell me. We don't go to conference. If you want to go to conference, I'll talk about the lab. You are dismissed to do the virtual lab. And then I give you a link to the homepage that will get you to the moduli that says online labs, so that you can record the HTTPS address. Then you are to exit Canvas. and go to the physics aviaries where all of those labs are from, except there's one at the bottom that's optional, and it's momentum. So, and I'm going to stay live, actually. I'm going to be here on my trusty little phone, and I'll be available until, I'll just say 9 o'clock. So if you encounter a situation, since I've been through all of those labs, of course, I can also go into the physics aviary and see what's happened. I could maybe give you some idea or what you shouldn't do or what you should do. So I'm here. I'm here when you're supposed to be doing the lab, which is during class time. If you elect to do it at some other time, I will be available from 10 to 10 on my phone, except for Sundays and Tuesday and Thursday night, because that's my other class. So if you have to do the lab on Saturday afternoon because it's quiet and everybody's out of the house, I'll still be available. Now I'm homebound. I'm old enough that I have to kind of stay in my house, if you know what I mean with respect to the virus. And although when I'm in the backyard, I usually am quiet. I don't have my phone with me, but as soon as I get in the house, I know whether or not you had called me or left me a message. So most of those 10 to 10, I'll be available. Usually if you send me a text message, I can respond within 24 hours or sometime within 5 minutes. That's the way text does. Does that help a little bit?
Professor?
Yes.
What is the website for our labs? Are we using Pearson or WebAssign or Canvas?
All right, repeat that. I think somebody logged out and it beeped and somebody talked. Can you repeat the question, please?
Yes, ma'am. I'm so sorry, brain fart.
I think you asked.
The website is the physicsaviary.com, and it's the first link under labs.
Okay.
Oops, folks, it's 4:30. I'm going to have to call it quits here and get my supper. And in an hour, I've got another conference call. But let me remind you, I did expand our discussion into a real live calculus function. And other than that, just about everything that I covered is embedded somewhere in the homework directly. Can I sign off now, ladies and gentlemen?
Yes, ma'am. Thank you.
You said the labs.
Okay.
Yeah. Do we need her?
That's a good idea. Thank you. Thank you.
Guys, stop. Do we need you present while we're doing the labs?
No, that's yours. The labs are designed to be single person.
All right, thank you. Take care. I appreciate it.
Okay. I'll talk to each of you about 1 o'clock or after the quiz about 1:30 on Tuesday evening. However, I'm usually online by 12:30, and I try to open the conference. A few people were on at 1:45, and we did a little bit of messaging. So have a lovely weekend and stay safe and stay positive.
You as well. Have a great weekend.
Take care.
Okay, you do too. Okay.
Thank
All right, you're welcome. Bye-bye, everybody. I like that. The phone did good. My phone did good.